In Tutorial 3, Forecasting, I will be demonstrating 4 forecasting methods. I will be applying each of these forecasting methods to the same set of historical data, and in hindsight, I will be comparing their accuracy. I have made copies of the templates for each of these forecasting methods, and I have already entered the historical data into each of the templates. Beginning with the moving average method, a moving average with one period is simply the naive forecast. That is, each forecast is equal to the previous period actual data. A two-period moving average yields a forecast which is simply the average of the previous 2 periods, and so forth. Observing the forecast, the red line, you will see that as the number of periods increases, the degree of smoothing exhibited by the forecast also increases. Comparing the forecast with the actual data, whereas the actual data does have some short-term apparent random fluctuation, the overall pattern exhibited by the actual data is of trend or growth, and the greater degree of smoothing will limit the ability of the forecasting method to react to that long-term growth. Therefore, the most successful moving average forecasting method will very likely be with a very low number of periods and a very low amount of smoothing. Using the mean absolute deviation, that is the mean error, to measure the accuracy of the method, a naive method has a mean absolute deviation of 12.124. A 2-period moving average is slightly better, but the 3-period on up yields successively worse mean absolute deviations. Moving on to exponential smoothing. The exponential smoothing forecast starts out with one naive forecast, and each successive forecast is a weighted average of the previous period's actual data and forecast. That weight is determined by alpha, the smoothing constant. The range of alpha is from 0 to 1. An alpha of 1 results in the naive forecast, and an alpha of 0 results in complete smoothing, that is, the forecast never changes. As alpha is increased from 0 to 1, decreasing the amount of smoothing, we will attempt to minimize the mean absolute deviation. Changing the increment from 1/10 to 1/100th, it appears that the best we can do is a mean absolute deviation of 12.8 when alpha is in the range between 84 and 87. Moving on to linear trend, which is quite a different forecasting method. Linear trend is simply the linear regression equation fit to the original data. Whereas linear trend does exactly measure the long-term change, that is, a slope of 6.3441 per period, the linear trend equation is unable to react to short-term fluctuations. The linear trend equation is typically used with other methods which may measure seasonal or cyclical behavior. The last forecasting method hopefully will be the best of both worlds. It will provide a trend which will enable the forecasting method to react to the long-term change while still utilizing exponential smoothing for short-term fluctuations. Trend-adjusted exponential smoothing must be initialized. So let's initialize with a forecast in, let's say, period 5. First, we will compute the trend based on the first and the fourth period. From the first to the fourth period, the actual data grew from 139 to 170. So we will estimate the trend as being 170 minus 139 divided by 3 periods of change, yielding a trend of 10.33. That's our estimate for the long-term change. As you recall from the actual equation, 6.3 is the actual trend. Our forecast for the 5th period will be the actual data from the fourth period plus that trend. So we will initialize the method with a forecast of 180. The successive forecasts are quite complicated, so I will simply demonstrate trying to achieve the lowest mean absolute deviation by adjusting the two smoothing constants. The first smoothing constant alpha is for short-term fluctuations, smoothing, and the second smoothing constant beta is for smoothing the long-term trend for the method. Very quickly, it appears that the optimal we can achieve is a mean absolute deviation of 10.04, which is better than the previous two methods, with a smoothing constant for the short term of 0.7 and the second smoothing constant beta for the trend of 0.2. And that brings us to the end of tutorial number 3.